Hello friends, welcome to CEC live lectures. Dear friends, as you know that in chemistry we have started a series on aldehydes and ketone, and today we are conducting 7th lecture in the same series. In today's lecture, in this session of the lecture, we are going to discuss about Wittig reaction as well as alpha carbon involving haloform reactions. To discuss this topic, we have with us our subject expert, Dr. Aparajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry in Sri Aurobindo College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome.
Thank you, ma'am. In our previous lectures in this series, we have studied the nucleophilic addition reactions of aldehydes and ketones, as well as nucleophilic addition reactions to alpha beta unsaturated carbonyl compounds, that is aldehydes and ketones. And during the course of these reactions, what we've studied is that the site of reactivity in carbonyl compounds is the carbonyl carbon, which has a partial positive charge on it, and it undergoes nucleophilic addition reactions. In this case, I'm talking of classical nucleophilic addition reactions. Whereas in some compounds, what we found is that they also have another site of reactivity, that is hydrogen, which is attached to the alpha carbon. Now, what is this alpha carbon? Alpha carbon is that carbon which is joined to the carbonyl carbon. And this hydrogen is quite acidic, so that it can be given off with a strong base, resulting in the formation of carbanion. In this case, it is an enolate ion, but for the sake of convenience, we'll be talking about carbanion. So, in these carbanion reactions will involve reactions like aldol reaction, Perkins reaction, halogenations at the alpha position, and this forms a very important aspect of carbonyl chemistry, to which I think we shall be devoting at least 2 lectures, because we have to discuss also the reactions which are related to aldol condensation. To start with today, I would like to start with Wittig reaction. Wittig reaction is an example of nucleophilic addition reaction involving a carbanion, and this reaction is very important because in this reaction we shall be dealing with formation of alkenes by reaction of aldehydes and ketones with phosphorus lights. So what are we going to do today is we are going to start with the reaction. First, the reaction of the carbanions, which are good nucleophiles, and for this we will be starting the Wittig reaction, and then we shall be dealing with enolate ions, for which the enolate ion, if I talk of an enolate ion, then please remember the enolate ion is formed because an alpha hydrogen is acidic in nature. The hydrogen attached here will be acidic in nature, and it can be abstracted by a base, resulting in formation of this anion. And then this undergoes resonance to form enolate ion. Enolate ion is more stable since oxygen has a negative charge on it. So we shall be discussing reactions involving enolate ion, that is the alpha halogenation reactions of aldehydes and ketones, and then we shall be discussing today aldol condensation and crossed aldol condensation. But in the first half of the reaction, I shall be first starting with Wittig reaction. Now, what is a Wittig reaction and why is this reaction so important? In Wittig reaction, an aldehyde or a ketone is reacted with a phosphorus light, that this is a phosphorus light, resulting in the formation of an alkene and triphenyl phosphooxide. So what we find here is that in this reaction, why is this reaction important? We are getting an alkene, and the C double bond O of the aldehyde or a ketone is replaced by this part of the Lide molecule, that is with the C negative, and in this case this will be acting here as a carbon ion, and this phosphorus part reacts with the oxygen, resulting in the formation of triphenyl phosphine oxide. So if we look into the mechanism of the reaction, our first interest is to prepare the light. How can we prepare the phosphorus light? We do the reaction of triphenyl phosphine with a primary alkyl halide. In this case, we've taken methyl bromide, and this reacts by a SN2 mechanism to give us a intermediate. Now, when we look into this, what we find here is that the hydrogen attached to the carbon, which is attached to phosphorus, is acidic in nature, and it reacts with a strong base like butyl lithium, and the butyl group being a carbon ion, it is a strong nucleophile, or it is a strong base, and it will abstract a hydrogen from here, resulting in the formation of a phosphorus light. Now the question is that why is this hydrogen acidic in nature? See, if we remove hydrogen from this carbon, we are getting this intermediate, and this intermediate is stable because in this the negative charge on the carbon can react with the positive charge on phosphorus. So this is a stable base. Hence, this hydrogen is acidic in nature. And now when we look into the structure of the light, then what we find is that in light, two atoms, that is phosphorus and carbon, which are directly bonded by a covalent bond, have opposite charges on it. That is, phosphorus has a positive charge and carbon has a negative charge. And the octet of each is complete. Then because of resonance between the negative charge here and the phosphorus, we can have this structure also. But this structure is neutral, whereas this is not neutral, this structure is uncharged, whereas this structure is charged. So this is more reactive structure. And when we talk of the Wittig reaction, of the reaction of this with a aldehyde or ketone, we shall be concentrating on this reaction, this structure, resonating structure. So now what happens is, after we've got the light, we will do the reaction of the light with an aldehyde or a ketone. So as I've said in the beginning, that the reactive site in these compounds, that is aldehydes and ketones, is the carbonyl carbon. So this carbon has a partial positive charge on it, and oxygen has a partial negative charge on it, because oxygen is more electronegative. Now this phosphorus light reacts through the negative charge on the carbon, and this carbon is now acting as a nucleophile, and it makes a bond with this carbon here. At the same time, what happens is there is electrostatic attraction between the carbonyl oxygen, which has a negative charge on it, and the phosphorus, which has a positive charge on it, resulting in a bond formation between oxygen and phosphorus. This gives rise to a betaine intermediate. This intermediate is also known as oxaphosphetane intermediate or a betaine intermediate. So what you have to observe further before we proceed further is that what we observe here is that in this case, 2 electrons are being contributed by the light here, and the 2 electrons are being contributed by the carbonyl oxygen here. So we can say that this is a 2+2 cycloaddition mechanism. That is, 2 electrons are coming from the light, 2 electrons are being contributed by the carbonyl compound. When we get a cyclic intermediate, so it is a cycloaddition, which is a betaine intermediate. Now this betaine intermediate dissociates to give us triphenyl phosphine oxide and an alkene. How does this bond cleavage takes place here is that this oxygen being more electronegative as compared to this carbon, and here this carbon here is more electronegative as compared to phosphorus. So what we find is that this oxygen pulls the electrons towards itself, resulting in a double bond between phosphorus and oxygen, and the bond cleaves from here, resulting in formation of triphenyl phosphine oxide. At the same time, the carbon being more electronegative pulls these electrons towards itself, resulting in a double bond between these two carbons, and the formation of alkene is facilitated. So what we find here is that this is a very good mechanism for preparation of alkenes, because these reactions are regioselective. That is, we will get only one alkene in this. So if I have to simplify the reaction, what can we say is that we will break the bond between the carbon and the oxygen and replace it with a bond that is the double bond of the aldehyde, which is bonded to carbon. So what if I see what we do here in this reaction is, that is, this bond oxygen is removed from here, and this carbon which is coming here, this will be bonded by a double bond to this carbon, resulting in the formation of an alkene. And the second thing that we have to remember is that the groups that I've shown in red color is the alkyl group, which is coming from the phosphorus slide, whereas the carbons which have been shown in black are the ones which are coming from the carbonyl compound. So if they do not ask us the mechanism, what you have to remember is you have to simply break the bond between carbon and oxygen, and we will attach this oxygen to this phosphorus moiety here, to the phosphorus, triphenyl phosphorus, resulting in the formation of triphenyl phosphine oxide, and the alkyl portion with the carbon having a double bond will be attached to the carbonyl part from the aldehyde part, resulting in the formation of an alkene. The best part about this reaction is, normally if we are preparing alkenes by dehydration of alcohols or by dehydrohalogenation of alkyl halides, we normally get two alkenes. One which is the more substituted alkene, and generally the more substituted alkene is the major product, because that we know is more stable and is the major product. Whereas if we want to prepare a less substituted alkene, then the question is little difficult. We can do Hofmann's elimination, that is, we do the reaction with a bulky nucleophile. But the best method to prepare only one alkene, that is, we are getting a high yield in Wittig reaction. So what we do here is, now if we look into these reactions, what we find here is we have taken cyclohexanone and we are treating cyclohexanone with Grignard reagent. Followed by, when we do this and followed by hydrolysis, what we get here is a tertiary alcohol. And when we do the reaction of tertiary alcohol, we dehydrate the tertiary alcohol. What we find here is that dehydration can take place in two ways, and we get one alkene, that is 1-methyl cyclohexene, and then we get methylene cyclohexane. But since 1-methyl cyclohexene is highly substituted, that is, to this double bond, there is a CH3 group, and here we have a hydrogen here. Whereas if we talk, and here we again have a methyl group, so that means this is more highly substituted. Whereas if I talk of this carbon is attached to two hydrogens, so it is less substituted as compared to this. So the major product formed is 1-methyl cyclohexene. Whereas when we do the reaction with a phosphorus light. That is, when we do the Wittig reaction, what we find here is that we have to simply break this bond, the bond between C and O, and replace it with a methylene group here, that is CH2 group attached by a double bond, and we will get exclusively this compound which is methylene cyclohexane. So in this manner, by Wittig reaction, we can prepare a alkene which is less substituted. So this is the advantage of this reaction. That is, we can get exclusively one alkene which is the least substituted alkene. Not only this, if I have not shown here, but if by chance a ketone is unsymmetrical, then the possibility is, that is, we may get two alkenes, that is the E alkene and a Z alkene. And please remember, Z alkene is more stable because the steric hindrance between the bulky groups is going to be going to be less there. Now, if I talk of a practical usage of Wittig reaction, then it has a very important use. We have heard of beta-carotene. What is beta-carotene? Beta-carotene imparts characteristic colors to carrots, yellow fruits like oranges, mangoes, apricots. This is all because of the presence of beta-carotene. Not only this, the color of flamingos is also orange because of the presence of beta-carotene in them. This beta-carotene can be synthesized from vitamin A by Wittig reaction. So what we do in this reaction is, we take vitamin A. In vitamin A, we have an aldehydic group, and we do the reaction with a phosphorus light. Now what you have to remember is that we have to break, this reaction is quite simple, we have to break the bond between carbon and the oxygen and make a bond between this part. When I say this part, that is, we are going to remove this triphenylphosphine, attach it to oxygen, when we will get triphenylphosphine oxide, and from this part we will attach this to this, that is, we will replace the oxygen with this entire moiety here, excluding the triphenylphosphine, and resulting in the formation of beta-carotene. You know, beta-carotenes are very important because it is believed that beta-carotenes are anti-cancerous. So nowadays, lot of people are concentrating on taking beta-carotenes. Now the next set of reactions that I am interested in discussing today are reactions due to the alpha hydrogen, which is attached to the alpha carbon. This part of the carbonyl chemistry is very important because we shall be making a carbon ion in this or an enolate ion, and then this enolate ion will act as a nucleophile and will undergo a series of reactions like alpha halogenations and aldol condensation that we shall be discussing today. So now what we find here is that what we know here, that if we talk of a ketonic group, then this carbon here, which is alpha to the carbonyl carbon, is attached to an hydrogen, and this hydrogen is acidic in nature because the carbonyl group is electron withdrawing group, and this hydrogen can now be abstracted, that is, the alpha hydrogen can be abstracted by a strong base, resulting in the formation of carb anion here. And please remember, this carb anion is more acidic. The carbon of this carb anion is more acidic as compared to a carb anion formed from an alkane. And we can say this hydrogen is acidic in nature because what we find is that this hydrogen is, why is this acidic in nature? Because when we talk of the resonating structures of the molecule, then what we can say is that this negative charge on this carbon undergoes resonance here, resulting in the negative charge on the oxygen. So here what I have done is I have shown the resonating structures for 2,4-pentane dione anion, and what we find here is that first, because we have got a carbon ion here, because this hydrogen was acidic in nature, this hydrogen is more acidic in nature as compared to this alpha hydrogen here. We have two alpha hydrogens here. One is this alpha hydrogen and the other one is this alpha hydrogen. And then this alpha hydrogen. These alpha hydrogens are equivalent, and this alpha hydrogen is more acidic because it is attached to a carbon which is sandwiched between two electron withdrawing carbonyl groups. And then what we find is that we can have more resonating structures for it, and this negative charge will go on to this oxygen, this carbon here, and this bond, pi bond, goes and it results in the formation of lone pair of electrons on oxygen with a formal negative charge on the oxygen. So this is resonance stabilized. Not only this, what we find is that the enolate ion, that is in which oxygen has a negative charge on it, is more stable because the negative charge is on more electronegative oxygen as compared to carbon. So these are hydrogens of the carbonyl groups are more acidic as compared to carbon ions which are derived from sp3 hybridized carbons. Supposing I say that is if I have a ethyl carb anion. Now when I talk of enolate, what I mean here is that an enolate ion has a negative charge on oxygen and then it has a double bond between carbon and carbon. And for the sake of convenience, we shall be doing the reactions with enolate ions, but we shall be referring them as carb anions in our lecture today. So what we have is that now if I talk of this compound, then what we have seen is that this compound at this position is losing a hydrogen, and then when it loses a hydrogen, it forms a enol form here. And because of the enol form here, we find that this can undergo, or because of the negative charge here, what we find is that it can undergo alpha substitution reactions at the alpha carbon. So now we have two forms. One is the enolate form and the other form that we have here is the enol form. So these compounds which form a enol form can undergo alpha substitutions at the alpha carbon. So now when we talk of this enolate ion, then what we find is that the enolate ion is an ambident nucleophile. That is, it can act as a nucleophile through lone pair of electrons on the alpha carbon. And second, what we observe here is that this is in carbon ion, it can act here. And if we look into the enolate structure of this, then what we find here is that oxygen has a negative charge on it. So it can act as a nucleophile from here also. But in most of the reactions, what we've observed is that oxygen being a strong base, it undergoes protonation. So it undergoes protonation at this place, and if it has to undergo nucleophilic alpha substitution, at this position, or it has to undergo nucleophilic addition reactions, then the reaction takes part from this carbon. So now when we talk of alpha halogenations, so what do we know of alpha halogenations is that the compounds which contain alpha hydrogen undergo alpha halogenation reactions. What happens in these reactions is that the alpha hydrogen is substituted by a bromine, Br+. That is, one electrophile is being replaced by another. Second thing that we know is that this can undergo this reaction via two mechanisms. It can undergo reaction in an acidic medium or in basic medium. In basic medium, this carbonyl compound has a tendency to form enolates, whereas in acidic medium it has a tendency to form enol. Then the next thing that we have to keep in mind is that the halogen atom that we can use in this reaction can either be chlorine, bromine or iodine, and you have to remember that the reaction can either be acid catalyzed or base catalyzed. So we shall be dealing with acid catalyzed or base catalyzed reactions. So what we observe in these reactions is that is whether we do halogenation in presence of an acid or a base, alpha hydrogen is replaced by a halogen atom, resulting in a formation of haloketone. And if we do the reaction in acidic medium, then only one hydrogen is replaced by a halogen. So what we've seen here is that when we do the reaction of cyclopentanone with bromine in acidic medium, one of the hydrogens is substituted by a Br electrophile, that is with bromo group. And in this case, since the ketone is symmetrical, so that means here and this position are equivalent, so we can either replace a hydrogen from here or we can replace a hydrogen from here. So we will stop here, and in the next section we shall go on to the mechanism of these reactions. Thank you.
Dear friends, in this session of the lecture, we have tried to understand the Wittig reaction as well as alpha carbon involving haloform reactions. On that note, we're going to take a break, and after the break, we will be resuming with our lecture. Thank you for watching. Hello friends, welcome to CEC live lectures. Dear friends, in this lecture on aldehydes and ketone, we are going to discuss in this session about alpha carbon involving haloform reaction, and we will also touch upon aldol condensations. To discuss this topic, we have with us the subjects by Dr. Aparajita Chauhan. And let's welcome Dr. Chauhan and ask her to resume the lecture. Welcome, ma'am.
Thank you. We'll take off from where we left. That is this molecule, that is, if I talk of a ketone, then it can undergo alpha halogenations. So when I talk of an alpha halogenation in an acidic medium, please remember only one hydrogen will be substituted with a halogen atom. Whereas when we do this reaction in a basic medium, then all the hydrogens at the alpha position will be replaced by halogen atoms. Why does this happen? That we shall be discussing. But now let us look into the reactions. So when I talk of a reaction, and if I'm doing the reaction of a aldehyde or a ketone with a halogen in acidic or basic medium, what we find here is that this hydrogen is replaced by a halogen, resulting in the formation of alpha haloketone. And this halogen atom can be chlorine, bromine, or iodine. And if we do the reaction with in a basic medium, then what we get here is we get again one hydrogen is substituted with a bromine. But please remember, here we've just shown one bromination, whereas we know that in basic medium, if we will take bromine in excess, then more of alpha hydrogens will be, that is, all the three alpha hydrogens of the acetone will be replaced with the bromine atom. So why does it happen that in acid catalyzed reaction, the halogen replaces only one of the alpha hydrogens? This is what we observe here. That is, when we do the reaction in acidic medium, only one hydrogen has been replaced. Now, and when we do the reaction of cyclohexanone, what we get here is 2-chlorocyclohexanone. The next reaction is, now what is the mechanism of this reaction? So what we find is, in the mechanism, the carbonyl oxygen will be protonated. When the carbonyl oxygen is protonated, it results in the formation of the enol. Now this enol acts like a nucleophile, and it will react with electrophilic bromine from the bromine molecule. What we say, when this double bond approaches the bromine molecule, polarization is induced in bromine, and bromine gets a positive charge which comes and replaces the alpha hydrogen, and the other bromine parts with the bonding pair of electrons. Now what we have is, we get a very acidic protonated carbonyl compound which loses a proton, resulting in the formation of alpha halogenated product. So now let us look into the mechanism with the help of reactions. So as I told you in the first reaction, please remember, whenever we do acid catalyzed reaction, this reaction is accompanied by enolization. That is, we'll get a ene along with the OH group. So now when we look into it, I've taken the example with acetone. So what happens is, in first step, protonation of the carbonyl oxygen takes place, because we know that this oxygen is basic in nature. It will pull the electrons towards itself because there is difference in electronegativity of the carbon and the oxygen, resulting in a protonated acetone. Now in next reaction, what happens is that because this oxygen has a positive charge, it will pull the electrons towards itself, as a result of which this carbon will now pull electrons from the alpha carbon, making this hydrogen acidic in nature. And now, since it is acidic in nature, it will be eliminated with the base, resulting in formation of a enol. So when we have an enol, so what is an enol? An enol is a molecule in which there is a double bond between two carbons, and OH is attached to one of the carbons which is containing the double bond. Now in this enol, what we see here is that the lone pair of electrons on the oxygen come back here, forming a double bond between carbon and oxygen, and this electrons here, that is the pi electrons between carbon and carbon, will now act as a nucleophile, and they will approach a bromine, or rather I would say, we can also say that when bromine approaches this double bond, polarization is induced here. That is, this bromine atom will have a partial positive charge and will act as an electrophile, and this bromine will now depart with the bonding pair of electrons. So what happens is, this pi bond makes a bond with this bromine, a sigma bond with this bromine, resulting in a formation of protonated halobromo compound. Now this is highly acidic and it will react with a base, and this H will be eliminated as proton, resulting in the formation of alpha bromoacetone. So this is how the reaction mechanism takes place. But please remember, when we are doing the reaction in acidic medium, only one hydrogen is being replaced with a halogen atom. If we want to do more halogenation, that is, we want to replace more hydrogens with a halogen atom, then what we find is that the successive halogenation reaction are slower than the previous ones. Why do you think this happens? If I go back to the previous slide, then what we find here is that this bromine is an electron withdrawing group. Since this bromine is an electron withdrawing group, it will pull the electrons from this carbonyl carbon. And when it pulls the electrons from this from here, what will happen? The basicity of the carbonyl oxygen decreases. And since the basicity of the carbonyl oxygen decreases, it cannot undergo this protonation step, that is the first step in the mechanism, very readily. Hence, after first bromination or after first halogenation, the reaction stops and it does not proceed further in acidic medium. Now let us look into the mechanism in the basic medium. So before going on to the mechanism of the basic medium, let me clarify two things. That if the alpha hydrogens can now be primary, secondary or tertiary, that is the carbon which is attached to the carbonyl group may have one hydrogen, that is two hydrogens, in which case it is a primary hydrogen. It can be attached to two carbons, in which I'll say that it is having a secondary hydrogens, and if it is attached to three carbons, it will not have a hydrogen. So please remember, alpha hydrogens, the order of reactivity of alpha hydrogens is that primary hydrogen is most reactive, followed by a secondary hydrogen and then a tertiary hydrogen. So what I mean here is that this hydrogen here will be most reactive. This will be less reactive as compared to this. So when we do the reaction in bromine, in excess of bromine and NOH, or here we are not taking excess of bromine, we are just taking bromine because we are at the moment discussing the halogenation reaction. So this is replaced, one of the alpha hydrogens here is replaced with a bromine, getting one bromo, two pentanone. Now these hydrogens which are attached to the carbonyl group are weakly acidic in nature, because please remember they will react with a strong base which is OH minus, which is coming from this NaOH, and will result in the formation of a carb anion. And this carb anion now will undergo resonance, that is this bond will go here and form a double bond, and this oxygen will pull the electrons towards itself, and since oxygen is pulling the electrons towards itself, oxygen will have a negative charge and we will have a double bond between carbon and carbon, resulting in the formation of an enolate ion. And please remember, enolate ions are strong bases and they are good nucleophiles. So I would like to show you the structure again once more of the enolate ion. So if I look into the structure of the enolate ion, then what we find here is that there is a double bond between carbon and carbon, and there is a negative charge on the oxygen atom. And please remember, enolate ions are strong bases and a good nucleophile. So now since we've got the slide with us, we can say that this is a carbon ion which was formed originally, and now this undergoes resonance with the pi bond of the carbonyl group. This becomes a double bond here, and oxygen pulls the electrons towards itself, resulting in the formation of a enolate ion. On enolate ion, we have a negative charge on oxygen and there is double bond between these two carbons, and it is a good nucleophile. So now when we talk of a base promoted halogenation, what you have to remember is in base protonated hydrogenation, the reaction will be facilitated or reaction will be started with OH. OH removes a proton from alpha carbon, forming an enolate ion. Now this enolate ion will react with electrophilic halogen and the other halogen atom will keep the bonding electrons. Please remember, we have not written here base catalyzed halogenation, whereas we are saying it is a base promoted halogenation. What I mean by saying it is a base promoted halogenation, that is during the course of the reaction, OH will not be regenerated, it will be used in the reaction. And the second point that you have to remember, a very, very important point that you have to remember is that when we've done one halogenation, after that the successive halogenations are going to be faster, or the reaction is not going to stop at monohalogenation, because the bromine, when it is attached to this carbon, will make the hydrogens more acidic, because bromine, being an electronegative atom, will pull the electrons towards itself, as a result of which the bond between the carbon and hydrogen will become weak. So let us look into the reaction, and what we find here is, when we look into the reaction, first, as I told you, the reaction will be started with the base. So in this case you have to remember that, and this base OH minus will remove a proton from here, and this bonding pair of electrons will go to this carbon, resulting in the formation of a carb anion. Now this carb anion will react with the bromine molecule. It is acting here as a nucleophile, and this hydrogen is acting here as an electrophile. This will make a bond with this bromine, and this bromine will depart with the bonding pair of electrons. And what we get here is alpha bromoketone. And these two steps, that is the formation of the carb anion and the reaction of the carb anion with bromine molecule, will take place 2 times, and both the other hydrogens will be replaced with the bromine atom. But what I observe in this case is we've taken 2 hydrogens here, that we've taken this as a methylene group, so that both the hydrogens will be replaced with a bromine atom. So this is the mechanism of the reaction. Now the question again, as I've told you, is they may ask you a question that why under acidic conditions aldehydes and ketones undergo monobromination, whereas under basic conditions they undergo complete halogenation. Then you have to remember is that when we talk of a base promoted reaction, then when a halogen is present here, it is more electronegative as compared to carbon. It will pull the electrons towards itself, as a result of which this carbon will now have a positive charge, and this hydrogen is more acidic. That is, the hydrogen of haloketone is more acidic as compared to a ketone, and this hydrogen will now be eliminated off as proton, resulting in the formation of this product. Now this will, since it has another hydrogen, it will again react and give us a tri-substituted product. So we see that if a halogen is present on alpha carbon, it will help in further halogenation reactions. Now we have to talk of the haloform reaction. Haloform reaction is an extension of basecatalyzed halogenations. What we do in this reaction is we treat methyl ketones or acetaldehyde with excess of halogen. which may be chlorine, bromine, and iodine in a basic medium. So when I'm saying we are doing the reaction in excess of bromine and base, what you have to remember is we are doing the reaction of one molecule of the aldehyde, that is acetaldehyde or methyl ketone, with 3 molecules of the halogen and 4 molecules of the base, which may be sodium hydroxide. Then the question is, why do we call this reaction as a haloform reaction? We call it as a haloform reaction because the product that we are getting has a halogen atom in it, and then it has 1 carbon in it, like we name formic acid. So from there we've taken form. So halogen is indicating that this molecule has 3 halogen atoms in it, and form means it has 1 carbon in it. We can do the haloform reaction either with chlorine, bromine, and iodine. And what we've already discussed in basic halogenation is that when we do the reaction in basic medium, all the 3 hydrogens, alpha hydrogens, are replaced with an alpha halogen, resulting in a formation of a trihalo group. This trihalo group is a very good leaving group because 3 electron withdrawing halogens are attached to this carbon. And then the cleavage of this haloform group is helped by hydroxide anion. And this reaction, as we'll be seeing now, is very effective for preparation of carboxylic acids from methyl ketones. Now let us look into the reaction. So what we find here is, like if I talk of a methyl ketone, so what you have to remember is this is an oxidation reaction. So when this is an oxidation reaction, please remember this part of the ketone, whatever it may be. It can be a methyl group here, it can be an ethyl group here. This will be oxidized to a salt of an acid. Whereas from this methyl part, we will get an iodoform or we will get a haloform. So when we do the reaction with excess of halogen in presence of excess of in a basic medium, what we find is all the 3 hydrogen atoms that are replaced with a halogen atom here. And when they are replaced with a halogen atom, it is converted into a trihalo group. And now this trihalo group becomes a very good leaving group. So now in the last step again, we have a OH which will help in the cleavage of this trihalo group, resulting in the formation of the carboxylate ion and a haloform. So similarly, now this was the general reaction in which we've observed. We'll quickly revise it. That is when we do the reaction with excess of halogen, all the hydrogens are replaced with halogen, converting this into a trihalo ketone, and this trihalo group is a good leaving group. It is cleaved off with the help of an OH negative, resulting in the formation of a carboxylate ion and a haloform. So if we do the reaction of acetophenone, which is a methyl phenyl ketone, with iodine in presence of NaOH, all the 3 hydrogens will be replaced with iodine, resulting in the formation of iodoform and sodium benzoate. So what we've observed in this reaction is that this part of the molecule has converted to a carboxylic acid and methyl has converted to iodoform. So this reaction is very useful for preparation of carboxylic acids from methyl ketones. So now let us look into the mechanism of the reaction. So what happens is, first in basic medium, halogen, this hydrogens, all the 3 hydrogens are replaced with the halogen atom, resulting in the formation of a trihalo ketone. Now in this trihalo ketone, this is trihalo group is a very good leaving group, And what happens in next step is that a hydroxide ion will come and react with this carbon, because this carbon is attached to an oxygen, and this oxygen will pull the electrons towards itself. Please remember, in the beginning of the reaction, when we started with haloform reaction, I told you that this ketone reacts with 3 molecules of halogen here, and what we've observed here is it is reacting with 3 molecules of halogen, and it is replacing 3 alpha hydrogens here. That is, an electrophile is substituting another H plus here, right? Now we are using, I told you we are using 4 molecules of NaOH. So what we find is, when we are using 4 molecules of NaOH, this carbon is reacting with one bromine, which is one atom of halogen, which is acting as an electrophile, and the second atom, as I told you, was given off as X minus. This Na reacts with that X minus to form NaX. So we have used 3 molecules of NaX in this reaction. Now what happens is, where is the 4th molecule of NaOH going? From the 4th molecule, we are getting an OH, which is now reacting with this carbonyl carbon, which has a slight positive charge on it, resulting in the formation of this alco oxide intermediate, tetrahedral intermediate. Now what we find here is, because this is which group will leave. Now this carbon, this intermediate becomes very unstable because it is attached to 3 electron. The carbon here is attached to 3 electron withdrawing groups, that is O, OH, and a trihalo group here. So now what happens is, between the trihalo group, formyl group, and the OH group, this trihaloformyl group is a better leaving group, and with the help of this OH, when this OH comes and makes a bond, does a nucleophilic attack on this carbon, this is given out, reacting in the formation of, resulting in the formation of a trihalocarb anion and a carboxylic acid. Now this carboxylic acid is acidic in nature, and this is basic in nature. So what happens here is, this being a strong base, eliminates or abstracts a proton from here, resulting in the formation of a carboxylate ion and the haloform. So hence what we see is, by this reaction we are getting a carboxylate acid and a haloform. So if I quickly revise the reaction, what are we doing? First we are doing halogenation, then the nucleophilic attack of the OH on the carbonyl carbon, elimination of the haloformyl group, and then haloformyl group acts as a base, as a carbon ion, and it abstracts a proton from carboxylic acid. Now the question is, are these haloform reactions, they are very useful reactions. But if I talk of, I am making a chloroform by doing the reaction with chlorine and NaOH, then we will get chloroform. Now chloroform is a liquid, so we would not come to know whether chloroform has been formed in the reaction or not. And if I am making acetic acid, again acetic acid is a liquid. So now what we do is, to make this reaction more practical, we do the reaction with iodine. The reaction mechanism is going to be the same. Everything is same. The only difference is that we will get yellow colored solid iodoform when we know that the reaction has taken place. So when I say the reaction will be same, we are doing the reaction with 4 molecules of NaOH, 3 molecules of iodine, resulting in the formation of first monohalogen compound, then dihalogen, and then iodo compound, and this will be facilitated by attack of OH on the carbonyl carbon. Ci3, being a good leaving group, will depart, resulting in the formation of we've not shown that step here, but then it will abstract a proton from the carboxylic acid, resulting in the formation of a carboxylate ion and iodoform. Iodoform reaction is of great use because we can use this reaction to distinguish between methyl ketones and other ketones. That is, a methyl ketone will give us a iodoform reaction, because please remember, it is from the methyl portion that we are getting iodoform, and from the other half we are getting the corresponding acid. So if I ask you, how will you distinguish between acetone and propanol? We can do the reaction with iodoform reaction. Acetone will give iodoform reaction. The other molecule, that is propanol, will not give iodoform reaction. And the second thing where we can make use of this reaction is if I have to distinguish between 2-pentanone and 3-pentanone. Now please remember, 2-pentanone and 3-pentanone, neither of them will give Felling's test or Tollens test. So how will we distinguish between these two ketones? Is by doing reaction, that is the iodoform reaction. So we have versatile uses of this. That is, we can prepare an acid by this reaction, as well as we can distinguish methyl ketones from other ketones. I hope this lecture has been useful to you, but you'll have to do a lot of practice to understand the concepts. And in the next lecture on this series, we shall be dealing with aldol addition, aldol condensation, and related reactions involving enolate ions. Thank you.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we're going to thank Dr. Aparajita Chauhan for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.